My most boring use of AI is asking it to rewrite an email I have been avoiding. Maybe yours is comparing two products or fixing one formula that somehow refuses to work. You type, get an answer, and close the tab. Done. It feels like nothing physical happened. While researching this, we pulled up an American electricity bill. It had energy, delivery, and taxes, but no AI fee, obviously. But now, look at what happened in the last few months. New York just paused state environmental permits for new hyperscale data centers. Federal regulators told 6 regional grids to address large load cost shifting. And 7 major technology companies promised to pay for the new power and upgrades their data centers require. Why are they all trying to solve a fee that supposedly does not exist? Because AI can push household electricity costs higher, but it can also pay its own way. The real story is who gets the infrastructure and who gets the invoice. The prompt is digital. The bill is physical. Okay, start with what is not happening. Your one prompt does not shoot through a cable and raise your neighbor's bill. It activates processors in a data center supported by cooling, backup systems, transformers, and a grid connection. Electricity rates are not calculated prompt by prompt. The important unit is aggregate demand. Millions of people, companies, and automated agents requesting compute across many facilities. Look at this. International Energy Agency page and notice 17%. Global data center electricity demand growth in 2025. Move down and the forecast says total use could roughly double by 2030, while AI-focused facilities triple. And here is the odd part. Power use per AI task is falling rapidly because the machines are becoming more efficient. But we keep finding more things for them to do. It is like getting a more efficient phone, then using it for everything. Efficiency lowers each task. More tasks can still raise the total. So the useful question is not, what did my prompt use? It is, what happens when billions of requests become a giant industrial load? Now, look here. This is Berkeley Labs' June 2026 update on U.S. data center energy use. The reference case says 649 terawatt-hours in 2030, about 11.8% of U.S. electricity. Put plainly, nearly 1 out of every 8 units of electricity used across the country would go to data centers. That is roughly 4.5 times the electricity used by the entire state of New York in 2024. That number sounds wonderfully precise, but it is still a forecast, not a promise. Keep looking. The uncertainty range is 9.5 to 15.3%. Chip shipments, server use, cooling efficiency, and AI adoption can move it. Also, data center does not mean AI only. The same facilities run cloud software, store photos, stream video, process payments, and support the internet. So AI is a major growth driver, not the entire load. The grid cannot wait until 2030 to learn which forecast was right. It must plan plants, transmission, substations, and transformers before demand fully arrives. And that is where a digital forecast becomes a physical financial decision. Your electricity bill looks like one number, but it is actually a stack. Energy produced, capacity kept available for high-demand periods, high-voltage transmission, and local delivery through substations and transformers. Look at this Energy Information Administration sentence. Prices reflect what it costs to build, finance, maintain, and operate power plants and the grid. Those 4 verbs are the bridge to your bill. Wholesale costs can flow into retail rates. Transmission charges may sit inside other bill items, invisible by name even when they change. Now add the part people usually miss. Forecast risk. Imagine a restaurant builds a second kitchen because one customer reserves every table for years. Then that customer arrives late or uses half the reservation. The second kitchen does not disappear, and neither does the loan. A data center can create that problem at grid scale. If a utility builds for a huge reservation and the customer uses less than promised, someone still pays. A strong contract keeps the risk with that customer. A weak one spreads it. The chain is AI use becomes a load forecast. The forecast drives market and infrastructure decisions. Rules allocate the cost. Only then can it reach a household bill. Prompt forecast. Infrastructure rules bill. Now, let us leave the analogy and look at a real market. PJM serves parts of 13 states and Washington, D.C. Its capacity market buys future reliability. On page 45 of PJM's Independent Market Monitor report, there is one number worth stopping on: $16.6 billion. The monitor estimates data center load increased capacity market revenues by about that amount across 2 auctions. It is a big number, and it needs an important warning. That is not $16.6 billion added directly to household bills. It is a counterfactual estimate for one wholesale market component. Fuel, weather, retirements, transmission, market rules, utilities, and regulators also affect retail prices. But PJM's following auction was the first in which the full region fell short of its reliability requirement, while more large data center loads entered the forecast. This does not prove data centers caused every dollar or the entire shortfall. It shows how forecast demand can tighten a regional market before supply catches up. Honestly, this is the section I expected to be boring: tariffs, contracts, and utility regulation. It turned out to be the entire story. There are 3 broad options. One is ordinary shared rates. Simple and the easiest way specialized costs can leak toward a wider group. 2 is a separate large load tariff. Virginia's GS5 class covers customers demanding at least 25 megawatts. Covered customers must pay at least 85% of contracted transmission and distribution demand and 60% of generation demand. So if the grid builds for your reservation, you cannot leave everyone else with the tab. 3 is to require new power, payment for delivery upgrades, and payment even when the full reservation is unused. A federal pledge signed by Amazon, Google, Meta, Microsoft, OpenAI, Oracle, and xAI. A pledge is not a power plant or a utility contract. It does not prove bills are protected. Its value depends on approved rates, genuinely additional supply, upgrade ownership, and what happens when a project changes course. That uncertainty is why FERC ordered 6 regional grids to justify or reform large load rules, and why New York paused permits while designing new standards. New York is not saying no AI. It is saying, decide who carries the risk before somebody pours the concrete. At this point, I have made a data center sound like the world's most demanding roommate. It needs power, cooling, backup systems, and maybe a new transmission line. That picture is incomplete. New projects can finance power plants and useful upgrades while supporting construction activity and community investment. More electricity sales can spread some existing grid costs, and long contracts can protect households from forecast risk. Data centers may also be flexible customers. Some computing can shift by hour or location, while batteries reduce grid demand during stress. The IEE says demand response can lower peak needs, defer investment, and improve resilience. Technology companies accounted for around 40% of corporate renewable power purchase agreements signed in 2025. AI demand is also supporting nuclear, geothermal, and storage. If chips, software, and cooling improve faster than usage grows, forecasts fall. If compute-heavy applications spread faster, they rise. This is where I changed my mind about the cleanest verdict. The data center itself is not the villain. A badly designed deal is. The IEA's conclusion is conditional with the right infrastructure and policy. More demand does not necessarily raise prices. Failure means building for a private forecast, giving the customer an easy exit, and handing others the risk. Now zoom out, because copying the American conclusion onto every country would be a mistake. Start with Ireland, where data centers used 23% of metered electricity in 2025, up from 5% a decade earlier. Circle 23, but keep the label. Ireland, not Europe. This is a high concentration case. Japan treats it as a location puzzle. Its watt-bit collaboration plans electricity, telecommunications, and data center sites together. Australia has 11 large projects representing 5.4 gigawatts of maximum demand in the transmission connection process. That is a pipeline, not operating load, and the distinction matters. The IEA expects data centers to represent roughly 5% of demand growth through 2030 across emerging and developing economies versus more than 20% in advanced economies. India's annual consumption is expected to grow by more than 570 terawatt-hours over 5 years, driven by cooling, industry, agriculture, transport, and wider access. A data center can strain one substation, but it is one claimant inside a larger story. So the US question travels, but the US numbers do not. Every place has to ask what is scarce, what else needs electricity, who funds the upgrade, and who gets priority when the system is tight. The next time somebody says AI is raising electricity bills or promises it never will, skip the dramatic number and ask 5 boring questions. They are much more revealing. Who pays for the new generation? Who pays for the lines, substations, and transformers? Does the data center guarantee payment if its demand forecast is wrong? Can it reduce or shift its load when the grid is tight? And after the construction rush ends, who keeps the long-term benefits? If those answers are vague, the cost has somewhere else to go. If they are written into a strong tariff and a long contract, the AI boom can finance its own infrastructure instead of quietly borrowing from household ratepayers. You may never see an AI fee printed on your statement, but the negotiations happening now in utility commissions, grid operators, state governments, and corporate contracts will decide whether it appears inside the total. The prompt is digital, the bill is physical. The rules decide whose bill.